Okay. Any questions so far? Hmm? Yeah.
So this d values of x,
The d values of x. Okay.
yeah, that's the degree values of x, or the degrees of x. Like the whole d values of x, it's, I know PA of x is equal to PB of x is polynomial, first polynomial is equal to second polynomial. But when you say d values of x,
Yes.
like how does it relate?
So we should do an example now, are we?
Okay.
Oh yeah. So what are we trying to do? We're trying to test if, let's say, a polynomial is two polynomials are the same.
Yeah.
Okay.
So if two polynomials are the same, if you subtract them from each other,
You
you
get
get
0.
0.
Yes.
So that other part where you're saying if you subtract them and you
They are
get
not the same.
another polynomial that is d values of degree something something.
Okay. So if they are the same, right? If they are the same and you subtract them, you're going to get 0.
Yeah.
But if they are not the same and you subtract them, you're going to get another polynomial.
Yes.
But that new polynomial that we're getting,
Yes.
we can say some facts about it,
Okay.
right?
Yes.
So even though we don't know what that polynomial is, we can already tell you things that that polynomial must obey.
Yeah.
So the things now are the degree cannot be more than the degree of the two things individually.
Okay,
Yes.
the degree cannot be more than the degree of the two polynomials you use in the subtraction.
Yes.
Okay.
So P of C, the degree of this polynomial
Yes.
is the maximum. So the maximum degree of this polynomial is the maximum degree of either A or B.
Of either A
Or B. So like if this was a degree 3 polynomial, this was a degree 2 polynomial, then this would be like a degree,
3 polynomial.
at most a degree 3 polynomial. It cannot be more than,
Okay.
it cannot be more than this.
Can it be less?
So the degree
It can be less.
of this polynomial can be less than or equal to.
Exactly.
Yes.
And then what do we say about degree? Degree tells you the number of roots
Okay.
in a polynomial, right?
Yeah.
And the roots are the things that when you evaluate a polynomial at them, they give you 0, right? So if we're saying that this has a maximum degree of 3,
Yes.
it means that there are only maximum of 3 points
Yes.
that if you evaluate P of C at,
Yes.
you will get 0, right? Maximum of 3.
Okay, that's the d values of x.
So those are now like, so those are the d values of x that when you evaluate that at those values, you're going to get 0, right? And it's only 3. It cannot be more than 3, right? You're not going to get 4 zeros. You're not going to get 5 zeros. Does that make sense?
Yes.
So if you now understand that about P of C, you can now use that to tell you certain things about P of A and P of B, right? So we're saying that let's say there are 3 spots in P of C that you get 0. What must happen when you are doing this subtraction for you to get 0 at those points? You know you got P of C from P of A and P of B. And when you are doing subtraction, what you are doing is that you are subtracting the evaluations of the polynomial. Let me prove that first, because that might not be clear. So let's say P of x is equal to 2x plus 1, and P of b is equal to 3x, right? If I should subtract this, I'm going to get what? 2x plus 1 minus 3x, right?
Yeah.
Which is equal to 1 minus x,
Yeah.
technically, right? Now let's do the evaluations of this. Let's say the first 3 evaluations of this. So if I evaluate at 0, that's what? If I evaluate at 2, that's what? So if I evaluate at 1, 3. And if I evaluate at 2, so this evaluation at 0, 1, 2, right? Then likewise this one, if I evaluate at 0, that's 0. 6, right? Now we already know that this is like 1 minus x. Obviously this goes down, right? Infinitely. But now let's evaluate this 1 minus x at 0, 1, and 2. Evaluate at 0, that's what?
1.
Evaluate at 1, that's what?
0.
Evaluate at 2, that's what?
-1.
Now you can see that it's similar to 1 minus 0. 1 minus 0 is what?
1.
Did you get?
Yeah.
1 minus 0 is 1. 3 minus 3 is what?
0.
And 5 minus 6 is what?
-1.
You can see that this is it.
Yeah.
So another way to see polynomial subtraction is just seeing like the evaluations are just subtracting each other at all the different values of x. So that's what polynomial subtraction is doing. It's like it's just subtracting them at all values of x. But now, this P of C, right? We're saying that it has 0 at 3 locations, right? So that should tell you something about P of A and P of B. They must have been.
Equal root.
They must have equal evaluations at those points, right? So let's imagine that this was how it was. That there was a 0 here, then there was something here, there was also something here, then there was a 0 here, and then there was a 0 here. That means that these points where they are 0, they must have been the same,
Yeah.
right? Let's call this one A and A. This one, they won't be the same, right? So let's just call this one B and C. And then this one D and what? E. But here will be the same, right? So this instantly tells you that if this one can only have 3 zeros, then it also means that these two can only agree at 3 points. So there's a maximum number of x values that will give you the same evaluations. Like this other one could not have agreed, because if they agreed, then that would have been 0 also, which will violate the degree thing, right? So two polynomials, if they are different, can only have the same values at d points. Does that make sense? Like, is there any question? This is-
D is the degree of the resulting polynomial.
Or you can think of the maximum degree of like t2.
The maximum of the two.
Yes. No, it's not exactly, but that's like a bound. You cannot go past that.
But looking at that example that we just used, can we like put it
So now in this example, yes, let's try this. But this example is too simple. It's too simple. It's better to do something like a quadratic example, but let's just see this now. So this was degree what? Degree 1, degree 1. Meaning that the answer is going to be degree 1 max, right? So if we're saying that, then that means that this one can only be 0 at what? 1 point, right? So if it can only be 0 at 1 point, it means that these two can only have one x, that both of them will give you the same y when you evaluate it, right? Because that's the only point that when you now subtract them, you get 0. So what we're saying now is that these 2 points only have one x. And to find that one, you just do like 2x plus 1 is equal to, and you solve for x. That will give you the points that, and that's the only point. Right? So x equals to 1. If I raise at 1, that's what? 3. If I raise at 1, that's 3 also. This is the only point that you can evaluate both of them and to give you a 1. And it'll be the same. In this case, 3. But then this one, that also now means that when we evaluate this at 1, we're going to get 0. Does that make sense? So this will be like 2 into 1 plus 1 minus 3 into 1, right? Which is what? 2 plus 1 minus 3. 3 minus 3 is equal to 0. Is it clear?
I'm not evaluating as 0.
Yeah?
I'm not evaluating as 0, or there's no need to.
Zero will not give you zero.
No. Why do you think we need to?
No, like I was thinking maybe every evaluation like start from 0, then 1 and stuff, and it's based on number of degrees.
Yeah,
And
no,
since this one has 1 degree one, that would be like 2 evaluation points.
degree 1 means I can evaluate at any number.
At least you need 2 evaluation points, right?
And to be able to represent it, yes. But were you following this part?
Yes.
What I was just showing here was that since it's degree 1, degree 1, degree 1, then that means that there's only one point
It must be the same.
that must be the same. And I just try to find the point directly, right? Not like through random evaluations yet. But wait. So now there's a problem with this, right? We want 100% guarantee. That 100% guarantee comes at a cost. We need to evaluate it at D plus 1 point. Hmm? Yes, recording. I hope so. Yes,
That
recording.
D plus 1 point evaluation that we are doing
Yes.
is to determine if that polynomial is a zero polynomial, right?
It's determined.
Like the subtraction, if the
Yes.
subtraction is.
You can do it for the subtraction, but then you can also do it for the individuals.
But then you now said that they are equal if the evaluations at D points are equal.
Yes, it's the
And
same
then
thing.
you are now doing D plus 1 evaluation.
Yes.
To know, okay, why are we doing that?
Like there are
The
two.
reason why you said earlier for the D plus 1 was that if you want to know if it's zero polynomial, if you just do like D points, then it's possible that the 3 points are like the zeros itself. So to be safe,
They are the roots,
and
right?
you have to do extra one.
Plus 1. Yes.
And I said that instead of that, now we can now do it for each of them.
You can evaluate both of them. So what I'm trying to tell you now is that there are two ways to test if two polynomials are the same. So the first test is that you subtract, right? You subtract them from each other, right?
Yeah.
And then you're going to get a new polynomial PC of x, right?
Yeah.
This polynomial is supposed to be 0. So all you need to do is evaluate this at D plus 1 points and make sure all the answers are zeros, right?
Yeah.
Right?
So this is a different method.
This is
from-
one way to test.
Okay. So it was.
But then based on this way, you can derive another way to test
Okay.
by looking back, right? The only reason why there'll be zeros is if the two of them align, right?
Yeah.
So that means another way to test is by evaluating P of A at D plus 1 point. Also evaluate P B of X at the same D plus 1 point. And if they are all equal, then that means the two polynomials are the same.
This is the same thing we're trying to achieve by subtracting.
Exactly the same thing.
When it's not more D plus 1, it's now D. So it's not more D points, now it's D plus 1 point.
It's still
Or we need D plus 1 points
to
put them
exactly.
equal at D points.
you can, it's so abstract. Like it might be hard to like really like wrap your mind around it. But D points what's the easiest way to explain this?
Okay, do you mean that like that difference comes in where if you have two polynomials that are not equal and get a polynomial subtracted, that polynomial, the given polynomial, like these two polynomials that you subtracted, you can like that degree, let's say the degree is 5, you can have 5 values of x, these two polynomials are going to get the same thing.
If they are equal,
Yes.
Mhm.
But if they are not equal,
if they're not equal, there's a chance that they might be the same at 5 values. Yes.
that's
So the only way to know whether they are really the same is by evaluating it at 6 values. So those 5 values that you pick might be the roots of P of C.
But that means D plus 1 is supposed to be a non-zero value.
if they are for P of C, right? Yeah, you're supposed to get a non-zero. It's guaranteed that you get a non-zero value because the degree already like puts a bound on things.
I think we need the points.
You need an example.
No, I'm just saying. Yeah, we do need an example. But I think we need the points when we want to say they should not be equal. Then we need the plus one to say they should be equal.
Say you need D plus D points.
We need the points to say they should not be equal. Then we need the plus one to say they should be equal.
It's always you. How do I put it? D is the condition. D is like the bound. D is the thing that is the limit. D is like if they're not equal, they might have the same evaluations at D points, but it cannot be more than D points, right? D is the limit, is the threshold. But then to now actually verify which one it is, you need to now test above the threshold. Like if they're equal, as many points as you want, they will always be equal. If they're not equal, then maximum of D. Do you get? So it is not sufficient to just test D, because that's the same case for both of them, right? This one contains D, and this one stops at D. So the way to know which one of them you are working with is to test at D plus 1 point. If it's not the same at D plus 1 point, you know you are working with the top case. But if it's different at one of the points, then you are working with the bottom case.
The degree we are talking about, is it the highest degree or the lowest degree?
Highest degree. I don't even know how will an example even work.
So this means that there is no two polynomials that are not the same, but that do not connect at more than D points. Is that what you're saying?
Yeah, if two polynomials are not the same, they cannot have the same evaluations at more than D points. Never.
Like there's none.
Cannot. And that's the proof. Yeah, set is 0. But that's like one polynomial. They're the same though in our case.
So anyone that has the same points at more than D points, that means they're the same.
Exactly. So if you have two polynomials and then they evaluate to the same value at more than D points, then those two are the same. If you continue, they'll keep on evaluating to that.
Yeah, so I think that no two.
It's not. You don't need to take it. It's
not they prove.
It's proven. You don't need to take it. It's proven. It's proven. Like.
No, what I'm saying is because I have a polynomial to degree 21.
Yeah.
Another polynomial to degree 18.
Yes.
And I'm not saying so meaning that there is no
They
way
they can't
not pass more than 18.
No, 21.
Similarities between
21. Use the maximum.
Okay, 21 as the highest one.
Yeah.
If they pass 21
And they are the same.
they are the same.
Yes. But you already know they're not the same because we already said that one is the 18 and 21.
Can we continue, please?
That's sure, I was just.
Yeah, no.
I'm not holding.
Don't mind him. Don't mind him. Okay, so how do we test this out? What would be a nice example to? You don't even need to find it. You can take two polynomials that are the same.
We already see they are the same.
No, we want to try both cases. When they are the same and when they are not the same.
I think when they are not the same, that's easier. So let's start from there.
Why is that easier?
Because you can just pick any two polynomial.
I mean, when they are the same, we are saying that it will look the same, right?
No, not necessarily. Not necessarily. But
We
it's
can
easier to
write
find.
one in a
It's
different
easier
way.
to find two polynomials than
That's
one.
ChatGPT
Can you ask ChatGPT?
I'm actually asking.
Two polynomials are the same, but look different.
Or look different.
Yeah. Two univariate polynomials are the same, but look different.
Let me ask.
So right now we're doing like 100% guarantee, but we'll reduce it. We'll reduce the guarantee from 100% down. It hasn't found one. You can't find any. There's reasoning. Is it dipstick?
Okay, so we have
X plus 2.
is equal to 2 minus 4. And the second one is x plus 2. Oh, this one is x plus x plus 2 plus 4. It makes it
It's not obvious. So I know what we could do. You don't tell me whether they're the same or not. Right? Don't tell me whether they're the same or not. Then I will tell you whether they're the same or not. With just one check. I don't know how to.
Okay, how about this?
Wait. Wait. He has given us one
Okay,
already.
okay.
And do your own.
Last time.
Okay, so now these are two polynomials, right? Not obviously, I don't know the case right now. I'm assuming they're the same, shall I call you? But now, we'll subtract them, right? So we could subtract them, or we could evaluate them separately. You said evaluating them separately.
That's faster.
What? It's not about fast. It's not about fast. It's still the same. It's the same. At the same time.
But it's no, it saves us.
We're not subtract. We're not simplifying.
Like if it's okay. Because if you subtract, okay, if you were to implement this, like you're still going to implement subtraction.
No, they're not implementing this. While leading to Schwartz-Zippel lemma, which is a fact that allows you to do certain things, like the oracle check and sum check, and shows that it shows you why that's like secure. So now, identity testing, Sha. We want to know if these two polynomials are exactly the same thing, right? Now, if we evaluate them at the same x, they should give you exactly the same y value, right? But then the only way that you'll be sure, because there's a chance that two polynomials are different, but when you evaluate them at that x, they'll still give you the same y value.
Yeah.
So you need to do it at d plus 1 point in order for you to be sure. The easiest way would have been for you to also get the roots, so that we can now use that to, yeah.
But the right one is the roots is complex. Not real.
Both complex and,
But this one is complex, like for the right.
is it all complex?
For the right,
Yeah.
yeah.
All.
Yeah, that's
So there's no roots whatsoever. No real roots.
No real roots for the one on the right now.
Which real roots?
On the right, there's no real roots.
like
There's no real roots for the one.
They can't be right because anything square will be positive,
Yeah.
and then it's always summing. So there's no real roots.
Yeah. For the one on the right, the root is 7.
Wait, now they might be the same now.
The one on the right, the one on the left, the root is 0 and
zero and then four.
I minus 4. 0. So, yeah, that's 0 and minus 4.
Zero and minus
Let
four.
us pick
For the right one,
Also, oh yeah, okay. Let us try evaluate it. Yeah? So you know the root, the root is a value that you evaluate the polynomial at, and you're going to get 0. So there are things called real roots, which are like irregular numbers. There are things now called complex roots, which are now from like the complex numbers. So that's like something like 2i. So if you evaluate the polynomial at 2i, you will get 0. But it's not like a real root because of the I.
He doesn't understand
I is equal to square root of minus 1. It's an imaginary number. But you don't need to understand everything right now. Okay, so let's just pick a random x, right? So someone should just give us x.
1 and 0.
So the degree is 2, right? That means that we want to evaluate at 2 plus 1.
2 plus 1 plus, yeah.
And they should both be equal, right? So that's we need one more. So the idea is that if we just stick to 2, there's a chance that they'll all be equal, but they're not actually equal. Because that D limit is. But then once we now put the last one, that will always like guarantee that.
Sorry,
Guarantee the case.
ChatGPT that gave us this. What was the premise? I think that both of them were equal.
Wait, don't tell us yet. So
Okay,
let's
you
find
know the
out.
premise.
Yeah,
Okay, just talk to me.
let's find out.
Why is there no x equal to 1?
No, you
No,
don't.
we can't pick
You can pick it.
You can pick anyone, any 3 points. So let's do 2. That's 4 square, right?
Yeah. I think you should put like LHS or RH like so we can distinguish.
Yeah, equal to.
Okay, you're doing both of them at the
Yeah.
same time.
Oh, okay. This is the left hand side. This is like I'm evaluating this one, and this one is the right hand side. So I just. Okay, so we're replacing 2 here, right? That's 2 plus 2, which is 4. That's 4 square minus 4. That's 16 minus 4, right? That's what, 12. Then right hand side, these examples are, it's not a good way to show this. That's why I was so running away from concrete. Like now, this is 8, right? The evaluations don't align. So instantly we already know that these polynomials are not equal. So we stop here. So what I really need is like, I need 2 polynomials that are not equal, and I need us to choose the x as the root. It's hard to find such an example.
So,
Uh-huh.
let's say x minus 1 x minus 2.
Mm-hmm.
X minus, then another polynomial x minus 1 is equal to x minus 2.
Okay. So yes.
Yeah.
I don't want to do it
We
here.
just need to expand this.
I don't want to do it on the
Go for.
okay. That was just it. When I was like we already know what this thing is. By the way, this is another way to write. So the roots of these polynomials are 1 and 2. Right? Because if you put 1 here, it will be 1 minus 1. 0, and everything will be 0. And the roots are the values that when you put them into the polynomial, you get 0. So this is what? This x squared minus. I don't know if this is correct though. Someone needs to. This one is so obvious that they're not the same. Huh? That's 6. But then they share roots. So this is degree. This is not it. This doesn't work. It doesn't communicate in any way whatsoever. Not that it doesn't work. Obviously we'll be able to do something, but it's not the concrete example that I'm looking. Yeah, if you rate at 1, they will get the same, right? So let's do that. Are you even going to get the same? You might not get the same. You actually will not get the same.
Actually,
Alright.
We'll get zero now. We'll get
Because
zero.
they have when you have three, they have root at one.
Yeah. But what I wanted is like you getting not zero.
When you get at three, you get zero.
Yeah, I wanted you don't get zero, but you get the same non-zero in both. I wanted the P of C to be the one that evaluates to zero.
Okay. Well, PLC is still into the zero.
0 minus 0. So let's say x is equal to 1, right?
Yeah.
Then x equals to 2.
And x is 3.
This is nice. I wish you guys were comfortable with just like algebra. So that I can just like prove it all the way down rather than looking for.
Let's
That's way now.
So it's like that is 0 now, right? This is not what I want to do. And probably let me think of how we can. What do we want to? What's the purpose of this calculus example? You want to know if two polynomials are. But that's not. I think the interesting thing is that you want to see two polynomials that are not equal, but they agree at D points. Yeah. And then you want to show that they agree at D points, right? And you want to also show that there is now no other point that polynomial can now agree at again, right? You want to ask Charity? Let's say degree two polynomials that are not the same. Huh? 2 degree 3. They're not the same, and they agree at D points. You have 2 polynomials. Okay. Do they have real roots or complex roots? Okay, just tell me the polynomials. You all have 3 roots. How many real roots? 3. Okay. Wait, let me see. What's yours?
X cubed minus 3x squared minus 2x.
Mm-hmm.
Plus 2x, sorry. And then x cubed minus 3x squared plus x plus 2.
Okay, what's yours?
X cubed minus 9x squared plus 26.
X cubed
Minus 9x squared plus 26x and then 24.
Ado.
And x cubed minus 8x cubed. 8x squared plus 19x minus 12.
Minus 5.
Minus 12.
Minus 12. Okay. Degree is 3, right? For both. Meaning that the maximum number of x values that they can be equal is 3. So, if we by chance happen to pick those 3 points, we will not be able to differentiate whether they're actually equal or not equal, right? So what we're now saying is that once we have picked these 3 points, the 4th one will always tell us which case we are in, right? Because we know they cannot be equal again unless they were actually equal. So, do you know the 3 points that we're supposed to evaluate yours that they'll be equal? You have to solve it.
Let me give you my own.
Do you have real roots?
Just look for
3 real roots.
It's 2 degrees.
Oh yeah, give it 2 degree.
X squared
X squared
minus 4 plus 4.
minus 4 plus
4.
minus 4x plus 4.
Minus 4x plus 4.
Okay. And what?
X S squared
Uh-huh.
minus 4x plus 3.
So now these two polynomials are obviously not the same, alright? But then the claim is that they can only agree at maximum of 2 points. They will never intersect anywhere else. So what are the 2 points now?
This one is S.
This one.
Like the first one.
It should be for both now.
Oh, that they have the same.
Eh.
Okay, I'm coming.
This is not hard. This is not hard.
I
That's
did
just
not, I did not know that that is
What
what
are we
you
looking for?
we're looking for 2 polynomials that are different but agree at. But we're also trying to find the D points that they agree at. Oh, you have one? That was fast. Okay.
So like they have the same roots, but not all the roots are the same.
Not that they have the same root, they have the same evaluations at the values of x,
That is not zero.
ideally.
Okay, S squared
Okay, x squared
plus 2x
plus 2x
minus 3.
minus 3.
S, the second one, S squared
Uh-huh.
minus 1.
Minus 1.
Yes.
Wow. So what's the first point we should evaluate at? Minus 1.
Yeah.
Okay. Then what's the second point we should evaluate at?
Huh?
What is the second point?
They must agree in the 2 points.
Yes.
And they must be degrees. So these 2 degrees are supposed to be 1.
No, it's two not.
No, it's two.
It has 2 roots, right? It has 2 roots.
The other one has to be.
Two of them have 2 roots.
It's minus 1 and 1.
Yeah, this one is
Minus 1 and 1.
This one is like
This one.
Minus 1 and
minus
3.
Minus 1 and 1.
and 3. Yeah, they are not the same. But both of them
You want
share
the-
one root. That's what I was asking him, like, what are we looking? Because it's kind of, the constraints are too much.
So the 2 polynomials must be different, but they must have the same.
So for this one now,
Oh, okay.
we need 2 more that I evaluate at.
So, what if the 2 polynomials have the same root, that means they are equal. So we're looking for 2 polynomials that they have the same root, but they don't have the same.
Because evaluating polynomials that have the same root, but if you evaluate them at the root plus 1, there will be difference. If you evaluate them at the root, there will be
They will
difference.
That's hard to find. That's going to be hard to find. That's going to be hard.
That was so algebra, please. I'll find it after. I'll find something after.
But
Yeah.
we're still in Schwartz-Zippel.
Yes, I want to now remove. I want to remove the 100%. I want to remove the 100% constraint. I want to reduce it down to. Oh yeah, no.
The polynomial, must they be the same degree?
Wait, they want to give us one.
Must they be the same degree?
It doesn't have to be.
Hey, it does not have to be. Okay, I have one. I was
Wait,
thinking that.
Francis, you have one. You think that it has to be the same? You say you have one. Oh, not now. Oh, you give.
I
Oh,
was thinking that the degree has to be the same.
you can pad it. You can always have. You can always make 2 polynomials the same degree, right? Like if it's, one of them is like x squared plus 5, another one is x plus 1. You can convert this to like 0x squared plus x plus 1, right? Technically, they're not like
Okay,
degree 2,
yeah,
degree
So
2.
I have
I have.
Uh-huh.
and one has like a root of 1 to 3.
Uh-huh.
Second one has a root of 1 to 2. You know, right?
Yeah, but I'm not looking for roots.
Oh yeah.
I have the equation. I'm just saying that.
Yeah, but when you evaluate the polynomials at those spots, they are all 0, 0, 0.
Yeah.
I want to know that when you evaluate them at those spots, they are not, they are non-zero. But then you know when you now subtract them, the P of C is now going to be 0. That's something I'm looking for.
That's right.
Don't worry. Don't worry. Yeah?
X squared plus 3x plus 2. Right?
And
X squared plus 3x plus
Okay, why am I not evaluating it all?
Evaluate at 1 and 2.
It's not possible for them to be equal now. That would be 1 plus 3 plus 2, right? Then 1 plus 3 plus 3. There will always be one greater than the other.
Sorry, sir.
You have one. Oh. X squared minus 3x plus 2 and 2x squared. Okay. Okay. Oh yeah, why should where should I evaluate?
1 and 2, okay.
1 now. Let's evaluate at 1. 1 minus 3 plus 2, right? And that's 0, right? I don't want to get 0. Wait, so will this work? 2.
Because they have the same roots.
They can't have the same roots though. Oh, they have the same roots with a factor. Yeah. So it's always, yeah, that will work. But they will give us, I want something that doesn't give me 0. But they give me the same value. You have 1. You want to try? Did you verify?
Yeah,
Okay.
X squared. The second one is.
That's all.
No, the second one is. The second one is.
That's all. That's x squared.
Yeah.
Okay.
The second one is X squared
Again.
plus
Cannot work now. Plus.
bracket is X minus 1 X minus 2. So we're looking at 1 and 2.
Right at 1, this is 1, right?
Yeah.
If I rate at 2, this is 4, right?
Yes.
Okay, this will work. Yeah, this works. Yeah, it cheats. You just need like x squared plus 0, technically. Yeah, this works. So what did we now want to do with this? But they are the same. They are not the same. Interesting. They are the same at 2 points.
There's 1 more point,
They are not the same. So regardless of the other 1 point, they will be different always. It's only these 2 that they can agree at. Let me try and... Okay, so let's try evaluating at 3 now. And let's say 2. No, I've done that too. Let's evaluate at 6. So that will be... And this one will be 36 plus something. And this other thing will always be non-zero. Right? So it's always going to affect the answer. So this is what 6 minus 1, right? Right? But how do I prove it to you now that there is no other value that will ever make them? Let's plot this thing. Right? Is it? After class.
No, there's no 3x plus 2. The first one is just x squared.
Oh.
Exactly, they align at those 2 points.
Oh.
So you see now.
That's 1.
They're here at 1,
And then the other one is 2.
and they're also at 2 or 4. Oh, it's 2.
2 exactly,
So it's here. So those are the places that they cut, that they intersect, I mean.
But they are not
But then they can never intersect any other, because they now start going in different directions and they will never meet anymore. So this is why like 2 polynomials. So if they are different but they are the same each degree, like you can know, if they are different, you can know how the maximum number of points that they can intersect based on the degree, the maximum degree. But if they are the same, they intersect everywhere, right? Like they're on top of each other. And this everywhere is a lot of points. Infinite. Compared to what? Compared to 2. That's where the power comes. If they are the same, they'll be same at an infinite number of spots. If they are different, they will only be the same at 2. Maximum of 3. No, of 2. It's degree 2. Yeah, these 2. So maximum of 2. Are you guys getting this? Like, if they are the same, regardless of where you evaluate them at, it will be equal. If they are different, there are only 2 places that you can evaluate them at that will be the same.
Because they are different.
Yes, that's if they are different.
Regardless of their degree.
It's deep points. Yeah.
And those two places are not converting.
You don't have to do. So let's now reduce the 100% guarantee, right? So I want to check that 2 polynomials are the same. P of A. Thank you. P of A and P B of X, right? One check that these 2 polynomials are the same. In order to do this, we need to evaluate both of them at what? D plus 1 points. And they must be equal. If they are equal at D plus 1 point, then they are the same, right?
But then, since you said they are equal, if the evaluations, like I think from that graph, that means they're equal. What I'm trying to figure out is why D plus 1 is sufficient enough to prove that they are infinitely equal. Like when you pick infinite number of points, they are equal. Is it through induction or that?
It's because of a degree D polynomial has maximum of 0, maximum of D zeros, right? So if a polynomial is degree D, then only D values of X will give you 0, right? Yes. That's the maximum of D roots. Does that make sense? Now, we now said if they are not equal, this thing will be a degree D polynomial. Which means that it will have only like D values of X that will make it 0. And this implies that these ones can only be equal at a maximum of D points. Because if it was more than D points, when we do the subtraction, we'll have more than D zeros at the other side. That's the proof. That because of this has a maximum of D zeros, instantly means that the other one has a maximum of D equal points. I don't know if you are seeing the proof. You are not yet seeing it.
I think it's
Step by
better
step.
to say that 2 polynomials are the same
Yeah.
if when evaluated at the same D plus 1 point, the D, because if you say D plus 1 point, right, you can say D plus 1 like 4 different points. So you can evaluate polynomial 1 at 4 different points that are not the same points where you evaluated polynomial 2.
That's about the same.
So I think it's the same D plus 1 point.
To compare.
Yeah.
I think we take it back to where we started. That to describe the polynomial, we know that
Exactly.
D plus 1.
So you
What-
know,
what?
there's always one polynomial. Like you need D plus 1 points to basically define one polynomial. meaning there will always be one polynomial that passes through d plus 1 points. Right? If you have another polynomial that can pass through that same d plus 1 point, it means both of them are basically the same.
Not necessarily.
Why?
Might have a higher degree.
If we have a higher degree, it still pass through the same point.
Yeah, but they're not the same.
But
Like
they're
because
not the same.
because they pass through the same point doesn't mean that they're the same.
Part of the same point and the event of it.
But like,
Mhm.
only
It's like interpolating. Wait, is this in writing now?
I'm using eraser.
It's working now, okay. But this was writing now. But this is not what I was drawing that time. Oh yeah. So if you could think of it as interpolation, right? So you could interpolate like 0 and 1, and then 1 and 2, right? You're going to get a polynomial, a straight line that passes through these 2 points. But you can also interpolate 0 and 1, 1 and 2, and then 2 and 9, for example, right? Now this is going to be a quadratic curve. Why this one is a straight line? But the two of them have like points that they intersect at. So this one has a higher degree. So that, but 2 degree, let's say degree 1 polynomials now. If it's the same degree, then only one unique one can pass through this. But when like you can have polynomials of varying degrees, then they might still be able to like share points.
Okay, so you are saying that you can have another polynomial that has 10 points, 10 evaluation points, but it's still degree 1 polynomial.
It's possible, yeah, that's possible.
No, it's still degree 1 polynomial. And we can have another polynomial that has 2 points, which is still degree 1 polynomial. But the two of them will be the same.
It's possible, yes. Exactly. If you get the remaining 8 points from the same line, then they are all going to be the same. Yeah. Which one? There's someone that draws with maths. Yeah, it draws with maths. So that you can draw like nature, a landscape. So this can be a polynomial, yes. I don't know if it will be one polynomial, but a mixture of like many smaller polynomials. I think he had a polynomial for like red, green, and blue. So that's like the colors, the RGB colors. And then he was able to evaluate it at all the pixel locations, and then he like drew it out, and then it draws like an actual picture. I'll find it. I'll send it to you. I don't know his name right now. Francis might know though. So wait, let's do this now. Right now, well, like the only way to be 100% sure is by testing it at d plus 1 points, right? Like we test both of them at the same d plus 1 evaluations and ensure that they're all equal. But is it necessary to, can we like relax that? Imagine if our degree was like 1 million, then we're still doing a lot of work, right? Testing at 1,000,001 points. So the question now is like, is it safe to test at just, let's say, 1 point? And how safe is that? It's no longer 100%.
And just put it around.
Yes. So, is it safe?
It's not going to be 100%, but we need the at least close to it.
That's what I'm asking you.
I think
No,
it's
it's not.
not.
It's not.
I feel like that one over the
except
degree.
If that point is not
as far as it's not part of the
It's not
So you have all the possible places that you can evaluate the polynomials at, right? Let's say this line, right? So you could pick this point here, let's say this is 0. You could pick this is 1, right? You could pick this is 2. All the way to, let's say like 1.8 billion or something, right? Now, you also have, so now you have two polynomials, P of A and P of B, right? Right? If they're the same, regardless of what you pick here, they will always be equal. So you're good. Now what if they are different? If they are different, there are some points here that you will pick that they will be the same. Those are the things that will deceive you. Like imagine if like once they are the same, you say they are the same. And imagine you now go and randomly pick that one point or one of those D points that they are supposed to be the same. You say yes, the two polynomials are equal, when in fact they are not equal. So the question now is like, what are the chances they are going to pick one of those D points by chance?
Like for two different polynomials.
They're just trying to pick one point.
Chance is very large.
But what's the exact distance? You know,
In one part,
yeah, one
Like
D over, exactly, D over D. So probability is usually like, let's say you're trying to pick from something. It's like the probability of picking the thing, probability of picking the thing over the total number of things you are picking. So now we know that it can only be equal at D points, right? So that means the top is going to be D over the total number of points you want to pick, which let's say is the size of the field. You know, in cryptography we use fields, so which is like a large space. So D over the size of the field is the chance that you pick one of those things that will deceive you. Yes, where they are equal. But then if your field is very large, this number goes down. Do you understand? Because the field is increasing, so the number is going down. So let's say you had only like, you had a degree 3, two degree 3 polynomials. That means they can only be equal by mistake at 3 points, right? Then let's say you had a field size of 17. This is not good enough, right? Because if you do 3 over 17 times 100, it means that 17% of the time you will pick one of those false points, right? And you will now think that the polynomials are the same when they are not actually the same. But you pick at D plus 1 point, you have 100%. That's like, there's a 0% chance that you are going to pick something that is wrong. So what we want to do now is we want to get this number as close to,
Zero.
yes, as close to 0 as possible. So there's a chance of like picking the wrong thing. So that's where you now like, you are increasing the size of the field in order to do that, or you are reducing the degree in order to do that, right? So to make this number smaller, you can either reduce this one or increase this one, right? But now if let's say your field size was now 1 million, that's now like 0.1234563% chance of you getting deceived, which is really small now, right? So that's like a 99.9999997% chance. So you can say that by increasing the field size, you are increasing your confidence level in just like picking one randomly. So that's why the field has to be big in order for it to get like its security.
Because sometimes the polynomials, the degrees are usually high.
So even if the degree is high, you need the field to be higher.
So does that mean here it will not be prime field? It will just be a field.
It could be a prime field, but a very large prime field. So like you saw all your numbers, when you printed out that BN254 or BLS, it was really large. It's because of something like this. Like that field has to be like really large for Schwartz-Zippel lemma to hold. Yeah.
Could this be efficient space-wise?
What do you mean?
If you have a polynomial that is quite high, we just keep increasing the field every time to.
No, the idea is that you already have a field that is really large, right? And because you have a field that is really large, you need to make sure that your polynomials don't grow above a certain size in the protocol. So let's say you wanted to do something like Fibonacci, right? You have a table of all the Fibonacci distances. You're going to convert that to a polynomial, right? And you know that the polynomial will have the same degree as the number of rows, similar degree to the number of rows, either plus 1 or minus 1, right? So all you need to do is make sure that the degree, the number of rows, does not get too big relative to the size of your field. So basically, looking at the size of your field, you will know like the soundness probability that you're looking for. That's like, I want my prover to catch a cheating, my verifier to catch a cheating prover 99.99999% of the time. Once you have the probability, so it's like x over, you know the size of your field, right? And you know what the probability is. So you can figure out what the maximum degree of your polynomials must be for this to hold, right? So looking at this both metrics, and I say, oh, the maximum degree my polynomial can be is like, let's say like 50k, right? That's the maximum degree of my polynomial. So all you have to do is that anything that is being proven has to be within this bound. And there are things that are called polynomial commitment schemes. Polynomial commitment schemes ensure that the degree is of a polynomial is within a certain bound. But the problem with this is that larger fields means slower computation, right? Because they're so big, numbers are so big. So it's slower, so your prover is slower. So the industry is moving towards small fields. Moving towards small fields, do this computation in small fields. But then there's something called a field extension. So there's a way to like increase the field size on demand. And then whenever you're doing something that depends on something like this, like Schwartz-Zippel, whatever, at that point you increase the field size. But the Schwartz-Zippel lemma basically is this. Two polynomials, if they're not the same, they will only be equal at a maximum of d points. Right? And then you can test whether two polynomials are equal by just sampling one random point from the domain and evaluating both of them at that. If it's equal, then with very high probability, the two polynomials are equal, right? Because of your field is way larger than the degree, so it's fine to just sample one. The chances that you will randomly pick is like being on the beach, right? And then you have grains of sand. The grains of sand are the places that you want to evaluate the polynomial at. Then imagine there are just like 5 grains everywhere that would make you think the wrong thing. It's safe to say someone should just go and pick one grain. Like it's just 5, right? It's just 5. But if you had just like 10 here, it's no longer safe, right? Because they might pick one of it. It's very likely they'll pick one of it. So that's like the kind of situation you're trying to create with Schwartz-Zippel. So it's a way to test that two polynomials are the same, but by only doing it, by only picking one guy. I'll send a video on this also that you guys can watch about probability testing and other things. Is that? Yeah, just error amplification. Yeah. So like if they are the same, there will be no error everywhere. But if they are different, then there will be errors everywhere. So as long as you can test for one error, you're good to go. Probabilistic polynomial testing, PPT. There's polynomial testing that is non-probabilistic. That's D plus 1 test. That's 100%. But then it's too slow, right? This one now is like it's always just evaluates at just 1 point all the time. But then you are sure because of the probability that most of the time, almost all the time, it's still giving you the correct answer. There's a very small chance, yes. 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 It's like the grain of sand thing, right? See how many grains are on the beach, and then only 5 of them will cause that sometimes. So it can happen. It can happen. But that's what ZK is trying to do. It's like regular computation is expensive, right? Regular computation is expensive. I'm going to find a way to do the same thing much faster or more succinctly. But then I'm going to give up some of that guarantee. It's a trade-off. I'm going to give up some of that guarantee. Because if you don't have this, then you always have to do the same thing. Prover and verifier always do the same amount of work. Then there's no point for having a prover and a verifier. You just do it yourself. But now it's like you're taking a computation that is symmetric and you're dividing it into 2 halves. So it's like It's like you have some computation that's like this. Without all this, if you want 100% guarantee, then both the prover and the verifier have to do exactly the same amount of work. And in that case now, there's no point in having a prover and a verifier. Just do the work yourself. But now with ZK, what this is doing is that it's converting this problem into two problems. The first problem is like this size. It's now way bigger. And then the second problem is now. So the prover does this, and then the verifier does this. But this is the same thing as doing this computation. You just split the work into. So you make the prover do more work so that the verifier can do less work. That's what ZK is doing. But then you now lose the 100%. But you can take that to as close to 100% as you want by just increasing the field size. Now, this is where multilinear polynomials now come in. Multilinear polynomials usually have lower degree than univariate polynomials. Multilinear usually have lower degree than univariate polynomials. So let's say we wanted to put 8 values in a univariate polynomial. That would be degree what? That would be degree 7. Right? But if you wanted to put 8 values in a multilinear polynomial, we'll use 3 variables, right? So f of a, comma b, comma c, right? And then the degree of a multilinear polynomial is basically just count how many variables are there. No, the degree of this is 3. Yes. So you can say that we're able to represent 8 values in a univariate polynomial, but it's degree 7. But this one we're representing it in a multilinear polynomial in degree 3. So when you do that d over this other one is going to, for the same data, it's going to be 7 over size of f, while this other one is going to be 3 over size of f. So this means that this field doesn't have to be as big to get the same level of security because the degree is smaller. So this means that you will now be able to write faster provers based on multilinear because of they are working with field sizes that are much smaller. Do you get? And then this thing increases crazily. So if you had like a million, that's like a million rows in your table, they are going to have a degree, let's say a million and one. A million and one, you're going to have a degree 1 mil, right? But for a multilinear, it's going to be like log base 2 of 1 million, right? And someone do log base 2 of 1 million. I don't know why this thing doesn't. I don't know what causes this. Okay. You see the difference? So the univariate polynomial will have degree 1 mil, and the multilinear polynomial will have degree 19. So one of them is going to be 1 mil over size of f, while the other one is going to be 19 over size of f. So this f can be like really small relative to this one. It will still be depending on your. Let's now assume that we want to do 99% security, right? So that means that when we do the division, it should be like 0.99, I guess. So we can solve for. To know the size of the field. Huh? Let me see. As you're increasing the field, the number is reducing, right? Probability of picking the bad value. Yes. 0.1. That's a 0.1. That's the one that is 90% probability of catching. Right? That's 0.9. So now what is the size of the field? The size of the field is going to be 1 million over 0.1.
That's 10 million.
That's 10 million. Then the other one is 1 million over, 19 over 0.1. 190. Can you see? So the size of the field for that other one has to be 10 million. Actually,
Interesting.
which allows the prover to be faster. So multilinear polynomials are what are leading to like the fastest provers right now, just because of the degree is much smaller and you can get away with using a smaller field size, essentially. So their field sizes are basically like they are as small as U64. So there's something called the Goldilocks field. Goldilocks field, like BN254 BLS. But this one, the numbers are regular U64 numbers. That's like just like your regular U64 that you can run on your computer. So it's much smaller than that like really large number. But it's still not enough. Like this 64 is still not enough for proving certain things because the degree is too close. So they now do like a degree extension, a field extension. So they do like, let's say, extension 2 or extension 3, which will basically increase the size of the field. But yeah, does Schwartz-Zippel lemma make sense? It's not supposed to make too much sense right now. I'll send a video, but I think it's the general idea. I don't know. Like even for like degree, you can find the roots easily for linear, degree 1. You can find it easily for degree 2. That's using almighty formula or quadratic. I think cubic there's a formula for it. But once you start going above like 4, there's no like analytical way to find the roots of those polynomials. So I think there might be something similar for like multilinear polynomials. To check that? Yeah, it's exactly the same thing. Like if you have two multilinear polynomials, you just evaluate two of them at the same points, and they should be equal. That's what you're doing in sum check. That oracle check that you're doing at the end. So that the prover has been giving you f of a, f of b, f of c, right? And then at the end of the day, you now do f of b comma c should be equal to f of c evaluated at r, right? You evaluate this one at r1, r2, r3, right? And you evaluate this one at r3. This is the oracle check. This is Schwartz-Zippel lemma in action. In the sense that these two polynomials are supposed to be equal if the prover was honest. So you are doing the identity check similarly. You are just picking one random point to evaluate both of them at. You know, the way the prover got this f of c is that he was putting in r1 and r2. You know, at the beginning, he started with f of abc, right? Then he gave you f of a, right? Then you now gave him r1. So you now replaced a with r1, right? And then he gave you f of b, right? But from this. Then you gave him r2. He replaced b with r2. And then he gave you f of c. So now this f of c is basically equal to r1, r2. But the only place left to replace is like r3, right? Yeah, c. So when you replace r3 here, you're supposed to have what? What's wrong with this? Yeah. I know it starts to, misbehave once it's there. So then this is now what? Once you evaluate it at R3, it's going to be f of what? R1, R2, R3. So if the prover was honest, then this is obviously the same, right? But if the prover was dishonest at any point in time, then they won't be the same polynomial anymore. And you can check if the two of them are the same by using the Schwartz-Zippel lemma. Just evaluate both of them at the same point, but pick it randomly. And then if they are equal, then the prover was honest, and the polynomials are the same, with very high probability.
So Schwartz-Zippel lemma is just the name for this term. It's not like...
It's the name for testing, yes.
Okay.
is the thing that justifies doing things like
Okay,
this.
so the oracle check is just Schwartz-Zippel.
The oracle check is using Schwartz-Zippel lemma. Yeah, is using the conclusion, like the Schwartz-Zippel lemma is what allows the oracle check to be secure. Like we can reason about the security. A protocol. It's kind of like a protocol. It's a protocol of testing two polynomials. That two polynomials are the same. Just evaluate both polynomials at a random point, at the same random point. If it's the same, then they are the same with a certain probability. So you need to look at the probability and make sure that probability is not too low. Right? Probability has to be a good probability. Does it make sense? You sure?
So,
Now, okay.
what was the Schwartz-Zippel lemma here? Okay. You said the last point was also evaluating about the 3 points.
Yes. If you write at R3, the circle is same thing as writing it at R1, R2, R3.
Yeah. So before we got here, how many points did we evaluate it at? That was 1, 2. The last C was at R3. Okay.
Which is the same thing as verify, just taking like the initial poly and evaluating it at all the challenges. Yeah. If you're honest.
Okay. What was it again? You said you must evaluate at 2 plus 1 point.
Yes, so if you want to be 100% guaranteed, yes.
Does it give us 100%?
This does not give 100%. This gives us degree over field size percent.
Degree over field size.
That's like
What's the field size?
depends on the field you're using. So you guys are you're using a very large field, even though you're working with like multilinear polynomials. So yours is like very, very super secure. But then Improver is slow.
Okay, so basically, I want to confirm this. So the lemma does not like tell us to use this big field.
It doesn't.
It just gives us the guarantee of 2 plus 100%.
It gives it's no. For example, lemma is like it's saying that I can tell you how secure your test is when you give me like your field size and the degree of your polynomial.
Okay.
It just tells you the probability.
Okay.
So you now have to put in the correct parameters to make sure that that probability works with the security level that your protocol is trying to attain.
Okay, so what you're saying now is both the 100% guarantee
It's technically
and the lesser guarantee, everything is Schwartz-Zippel lemma.
Schwartz-Zippel lemma is more focused on the
Not the 100% guarantee.
not really. So like say here now like D over. So it said it's a tool commonly used in probabilistic polynomial identity testing. But I'll send you guys the video though. Yeah.
Like then the reason why you made me, the reason why you said last week class, the oracle check is the major issue. Yes, the last time I was actually arguing about you giving the wrong polynomial. So the reason is because of this Schwartz-Zippel lemma at the final check. So if the final check is wrong, it means that
The prover did something wrong along the way. Like if the prover can be dumb and do something wrong and you catch them at the round poly checks, right? But then a smart prover would not be caught at those round poly checks. It will be at the oracle check. So you can catch them at different levels.
So there's something you said when we start doing PCS that there will be no need for the verifier to know the polynomial. So the prover can commit the polynomial and there is a way somehow that the verifier will know that the polynomial is
What?
there.
That polynomial is what?
That there's a way that the verifier will know that the polynomial that was committed is right or something, like without knowing the polynomial.
Like
So,
no, sorry. The prover has a polynomial.
yes,
The verifier wants to evaluate that polynomial at a certain point in the future.
yes,
So the verifier asks the prover to commit to that polynomial,
yes,
and they will send that commitment.
yes.
Then later in the future, the verifier can now say that polynomial that you have, evaluate it at 4 or evaluate at 5. So the commitment scheme ensures that the prover is not lying about the evaluation.
Okay. But the verifier doesn't know.
It still doesn't know the polynomial. So let's say the evaluation at 4 was 16.
Yeah.
So the prover will send 16
Yeah.
and will send a proof,
Yeah.
a polynomial commitment proof.
Yeah.
Then the verifier will just verify that proof and he knows that the evaluation is actually 16.
Where does he verify the proof?
In the verifier logic.
The verifier doesn't.
Yeah.
So what I'm asking, in our whole sum check process, the reason why the verifier was able to verify
Oracle check.
the oracle check and the process was because, when the prover committed the initial probe and the claim sum, the verifier in the process of doing those stuff to committed the initial probe and the claim sum, that way they'll be able to generate the same random challenge. Now, in the case of PCS, where the prover doesn't send the polynomial to the verifier, he just commits it to the PCS and all. So how does the prover now how does the verifier does his own verification without actually having the polynomial?
Yeah, so instead of committing the polynomial to the transcript, they'll put the commitment in the transcript. So right now the prover would take the polynomial, convert it to bytes, and then put it in the transcript. Then the verifier will also do the same thing. But in this case now, the verifier doesn't have the polynomial again. So they're no longer putting the polynomial in. They're now putting the commitment to the polynomial in.
What is the commitment?
The commitment is the commitment. It's like it's a field element, for example. Huh?
See, the commitment is what?
It could be like a field element, like a number. Commitment is very short. Like you fingerprint the polynomial as a number, for example.
Like the proof itself.
It's a commitment. I don't even know Merkle trees.
Yeah.
Merkle trees, there's a root hash at the top. Even though there's data.
Yeah.
That root hash serves as the fingerprint for the data.
Connects everything.
Exactly. So the same thing with polynomials. There's a way to convert the polynomial into like a small thing. That small thing is the commitment to the polynomial.
So Schwartz-Zippel Lemma doesn't play any role in this guy.
Schwartz-Zippel Lemma just tells you that you can check that two polynomials are the same by evaluating them at a random point. And this is how secure it is. D over field size. But that is now used everywhere in ZK. Almost everywhere. There is a premise that, yes. So it's like, in ZK, you'll get to the point where, almost every time you get to the point where you have a polynomial on the left hand side, and you have another polynomial on the right hand side. And whether the person was honest or not depends on whether these two polynomials are equal.
So this is where Schwartz-Zippel Lemma will play.
Exactly. So Schwartz-Zippel Lemma now say, you don't need to check everywhere. Just evaluate at 1 and you are good to go. So that's why ZK is succinct. Because of now the proof is just the single evaluation, right? Rather than a ton of evaluations.
How are we going to use it?
So now I want to now talk about that Fibonacci this thing that I was talking about last time. Yes, that one that I made a mistake at. So we're like, you have the Fibonacci sequence, right? 1, 1, 0, 1. 1 plus 1 is 0 plus 1 is 1. 1 plus 1 is 2, right? 2 plus 1 is 3. Don't stop here, alright? So we will convert this to a polynomial. So this is going to be like f of x, right? If you evaluate f of x at 0, you get 0. If you evaluate at 1, you get 1, right? This is interpolation that we all know. Right? So this is like the computational trace. And then this is you basically interpolating each other, representing as a polynomial. Because most snacks work with polynomials in mind. So what we need to do now is we need to create a constraint checking polynomial. So that's a polynomial that will check that you did everything correctly, right? What's the constraint? The constraint is that f of 2 should be equal to f of 1 plus f of 0, right? So once you create a polynomial that, if you did it correctly, it will give you 0. But if you did it incorrectly, it will not give you 0. So we can say something like f of x minus f of x minus 1 minus f of x minus 2. This will be 0 for all values of x if you did it correctly. So you will always have a range where, so like, you're not going to test, this was the mistake I made. I was saying that this will always align for all x, up, down. That's wrong. It's only going to align for x in the domain that we are actually did Fibonacci, right? Because these other ones might be random, okay? So let's test it out. Let's say we try to do f of 2, right? So that'll be f of 2 minus f of what? 1 minus f of 0, right? F of 2 is what? 1 minus 1 minus, which is what? So it passes, right? So this is like a new polynomial. We evaluated it somewhere and we got 0. It should give you roots. It should give you roots vibes, right? You're getting a 0 when you evaluate a polynomial somewhere. It should start giving you roots vibes. So let's try f of 6. F of 6 minus f of 5 minus f of 4, right? F of 6 is what, 8? Cool. So all the places you did Fibonacci, this will hold within this range. You stop at 7 and you start at 2. You won't do for 1 and 0 because those ones will be. So you create another constraint for those. Those are the boundary constraints. So, well, I'll answer the question. So like, you know that this constraint, right? It requires that you have two things above you. So it won't work for f of 1 and f of 0 because you don't have two things above them, right? So you have another check. Yeah, for 0 and 1. But let's now focus on just like this constraint checking, right? So that's f of x minus f of x minus 1 minus f of x minus 2. Let's call this c of x, right? So c of x is the constraint checking polynomial. It's the polynomial that will evaluate to 0 at all the places that you were supposed to have put in the correct values, right? And we have tested it with some. And you should be able to logically see from just looking at it that it will work for anything between 7 and 2, right? Now, there's something about roots of a polynomial. You can divide a polynomial by its roots, and there will be no remainder. I don't know if that's correct.
There will be no remainder.
Just like 0, 0, 0.
Oh, remainder, yes.
So we have showed two ways to write polynomials. You can write it coefficient form. You can write it evaluation form. There's another way to write it, root form. I don't know whether it's called root form. We'll call it root form. So this is the way you have already seen it in Lagrange, kind of. So if a polynomial has two roots, right? Let's say the polynomial has a root that is 2 and another root that is 3. You can write the polynomial x minus 2, x minus 3. Yes. That makes sense, right? Because of, if you put 2 here, it will be 0, then everything will be 0. That's a root. If you put 3 here, it will be 0, then everything will be 0. That's a root. So this is another way to write a polynomial. But then this now means that you can divide by any root, and it will always cleanly divide. Does that make sense?
Yeah.
You can also divide by, and it cleanly divides. And you can divide by a combination of them. and it cleanly divides, right? No remainder, just a quotient.
Yeah.
Make sense?
Yeah.
But then if you divide by a non-root, it won't cleanly divide anymore.
Yeah. For real.
You will get a quotient and a remainder. This is what they want to take advantage of. So now this polynomial has at least 1, 2, 3, 4, 5, 6 roots. Right? If you evaluate at 7, you'll get 0, right?
Yeah.
Because it will be 7 minus f of 6 minus f of 5, right? And then it will be 0. So 7 is a root. 6 is a root. 5 is a root. 4 is a root. 3 is a root. And 2 is a root. So the way you check that the prover has done everything correctly is by dividing that polynomial by all the roots. Okay? So you tell the prover that that c of x that you have, I want you to divide it by x minus 7, x minus 6, x minus 5, x minus 4, x minus 3, and x minus 2. Stop
All
here.
at once.
All at once.
What if c of x is just because at the end of the day, c of x, what is c of x?
Okay, because of it won't pass here. Now if you do f of 1, right? Minus f of 1 minus 1, right? Minus f of 1 minus 2. F of 1 is 1. F of 1 minus 1 is f of 0, right? And this one is now like f of minus 1, which is outside our computational trace. So we're not checking for that like constraint. Does it make sense? You wanted to ask something?
Yeah, no, let's just go.
Are you sure? Okay. So now if the prover did everything correctly, all of this would divide cleanly. Right? So we'll get just one value, which is q of x. Right? Quotient. We'll get just one value. But then if the prover, so what they call this thing, they call this the vanishing polynomial. The thing at the bottom. The vanishing polynomial. Basically, it's the points, these are the points where the thing at the top should evaluate to 0. So it should vanish, right? Does it make sense? So rather than writing it over and over again, I just want to use v of x. Does that make sense? So c of x, yes. So if you are honest, this should be q of x. So that means that you can have a left-hand side and a right-hand side. These two should be equal if you are honest. If you are dishonest, there will be a remainder. Yes. Chinese remainder theory. So now, Schwartz-Zippel comes again. So you now actually want to like verify that the left hand side is equal to the right hand side. So all you need to do is just pick one random point from the field and then ask the prover to evaluate C at that point, evaluate Q at that point, evaluate V at that point. When you multiply all of them together, it will be equal if it was honest. If it was dishonest, it won't be equal until it gives you R evaluated at that point. But you're not going to collect that, right? Because you are saying that you are supposed to be honest, so I should only need 3 values from you. Does it make sense? Yeah.
Yeah, I got the context for my question.
Yeah.
So, like, C of x
Yeah.
is a polynomial created from three
Yes.
values of x.
Yes.
And now we are trying to divide it with a polynomial created from like 5
As many as
values
you
of
want.
x.
Yes.
And then we are saying it's going to divide cleanly.
Yes.
No, you see, C is the polynomial created from what?
3.
How is it? It's not the whole
It's talking about the.
I'm talking about what
C
you
of
think.
X. C of X is the polynomial representing the Fibonacci.
Yeah, like it's the
C
equation
of X is the
that's
polynomial that checks that the Fibonacci was done correctly.
So
F of X is the polynomial representing the Fibonacci.
So how did you now get C of X?
By now creating a polynomial that checks that the Fibonacci was done correctly.
Okay, using this.
Yes. This is C of X.
Okay.
and now we are dividing it with
So like you put your data in a polynomial, then you create another polynomial that checks that the data is well formed.
Using some constraints.
Using some constraints,
that
yes.
ensures the certainty of that. That preserves the property of that. First.
Whatever it is you are checking, right? So your data is somewhere, then you have something that can check that your data is correct. That's like that you did the computation correctly or whatever. That's C of X. Then that C of X now has like multiple, let's say like this one is checking multiple Fibonacci's, right? So that's why we're dividing by multiple points. Like all of those places should to be fine. All of those places should 10. Evaluate to 0.
So
because
C of X is basically the pattern of generating the consecutive f of X.
Fibonacci, right?
Yes.
Yes, for example. I'm generalizing. This works for any problem.
because like what's coming to my head is let's say the root.
So what you're trying to do is like, you're trying to create a polynomial such that if you did things correctly, that polynomial will be 0 at all those places that you did things correctly.
So meaning that this 1, 2, 3, 5, 8, 13 are the roots of C of X.
No? It's 2, 3, 4, 5,
Like
6,
1,
7.
2, that's what I'm like. I'm sorry, I was reading the wrong value.
Yeah, X is going to be the
Number
root. Yeah.
All of them are the roots
Yes.
of
Yes.
that's C of X.
Because of C of X will vanish, or C of X will result into 0 at all those evaluations. Like that's how we structured it, right? That this one minus this one minus this one should be 0. So 7 will give you 0. Then you can check that all of them vanish by just dividing it by the vanishing polynomial.
So why is this called stack polynomial?
So stacks, this is how they do their, how do I put it? Their stacks are based on univariate polynomials.
Stack.
Yes.
Okay, stack and snack. Is it
There are some
stack
snacks that are
is
based
it-
on
is it
univariate.
stack like stacking or stack like
No, stack,
opposite of
stack
snack?
way.
Okay, stack
I won't say opposite of snack. Right now, it's more like snack is, they might crucify me for this, but snack is like the family. I've seen, but stack is now like, yes. If some people hear this thing, I don't vex. But it's the truth. It's the truth. So say it with care. It's like tabs and spaces. Yeah. So this is how I say it.
The stack uses univariate.
Is
By
that,
stacking.
yeah. Thing stack, that's transparent. So this is the problem. Before, in the old, when I say old, just like how many years ago, there was all snacks were usually based on something called there's a trusted setup. There's something called a trusted setup. The trusted setup like sets things up, but it's not safe. Like that's why the trusted is there. In the sense that usually what happens is that they generate a secret. That secret, if anybody has access to it, you can always generate a false proof. Right? So it's called toxic waste. So but that waste is needed to set up the process. So what happens is that they need to generate that secret and then someone needs to throw it away. And he himself must not remember what that secret was. So it's trusted. It's a trusted setup. But then Starks came in saying, you don't need that trusted setup. I have a different way to do it. That's where the transparent is. Like the setup process is transparent. Anybody can see what is happening. But in the old Snark, it was not transparent. It has to be hidden. So there are things like NPC and all those things that they use for trusted setups.
Yeah.
You guys might do trusted setup for like KZG. One wants to do like multilinear polynomial commitment schemes. So you do a trusted setup for that.
Let me just answer.
Yeah.
Basically, everything here is people. This basically the case in
How?
This stuff, what it does. So pay attention. The polynomial commitment scheme. This is basically what is based on. Like everything you just said is what like polynomial commitment scheme.
You're like 2 steps away from a polynomial commitment scheme.
Yeah. That secret this thing is just the point you want to evaluate the polynomial amount. That toxic waste is just the point you want to evaluate that polynomial amount. That's relating Shamia share.
Not really.
But you made mention of NPC.
Yes. So NPC is like a way to generate the. So normally like toxic waste is generated by one person, but that's too much trust in one person. So there's a way they now do it that they can have like 50 people work together to generate the toxic waste. But then all of them are generating like parts of it. So as long as one person deletes their own honestly, then it is safe. Because in order for them to recover it, all of them have to come together to recover it. But if one person is honest, then the entire protocol is honest. Kind of.
Sorry, did you say KCG was trusted?
KCG is based on the trusted setup, yeah.
Because not ZK, but like I remember when we were doing this setup for KCG commitments on Ethereum.
Yes, exactly. That's NPC.
That was NPC, exactly.
Yes.
So that's not trusted.
It's trusted. It's still trusted. Like technically, everybody that is doing it could keep their share, right? And then come together. Very unlikely though, but it's trusted. But then there are non-trusted setups where you don't even have to worry about all those.
So you say Stack also uses NPC?
No, Stack is this. That T there is transparent for the trusted. There's no trusted setup in Stack.
Okay.
Yeah.
So I'm still particular about. You just said the reason why you call this Stack 101 because Stack used to be very.
I won't call it Stack 101 per se. This is like quotienting. Yeah. But Stack 101, if you watch Stack 101, it's basically this. But then they now bring in Fry. Yeah, they bring in Fry for their polynomial commitment scheme. But then they still do like quotienting. So there are like a series of techniques that just exist, like quotienting, then PCS. Stack has their own PCS, which is Fry. We're going to do Fry too. PCS, polynomial commitment scheme.
So can you explain that C of X again? Like
C of X.
yeah, that's C of X. You said dividing by that vanishing not give us a remainder. So I'm like, but this C of X was equals to F of X minus F of X minus F of X minus 1.
C of X is equal to F of X minus F of X minus 1 minus F of X minus 2, right?
Yes. So my question now is, if we divide this,
Yeah.
literally by X
Minus
X
7.
minus 7 down to X minus 2, X minus 2.
Yes.
Oh yeah, X minus 2.
Yeah.
If we divide literally X minus 2, will it vanish?
It will give you something without a remainder, yes.
Or
The
is
reason-
it without a remainder, okay.
Yes. It won't vanish, but it will give you a quotient.
Without a remainder.
Yes.
I thought you should give one since you are dividing with all values of.
No, that doesn't mean that those are all the roots.
Please, wisdom. we recording?
I don't know. I just hope so. There's audio, sure. So you're saying like the application of Schwartz-Zippel kind of, in the sense that once you now have this, you can kind of like compare by just evaluating at one. You evaluate left hand side at one point, evaluate right hand side at one point.
But at the end of the day, we have to try to get the vanishing point.
You already know it now. Like let's say you told the verifier told the prover that I want the first 20 Fibonacci numbers.
Oh, so it's going to just be dealing with Fibonacci numbers.
No, not necessarily.
Oh, that's just an example.
That's just an example.
Okay.
But I'm trying to show you that the verifier knows what V of X is supposed to
Yeah,
be.
go on, please.
Yeah. So it's like the verifier said I want the first 20 Fibonacci numbers. So that means he knows that the vanishing is going to be like at 20, 19, 18, all the way to 2. Yeah, so he knows what V of X is. Yeah.
So
But
how about the quotient? How does he know the quotient?
It doesn't know the quotient now. It's the prover that knows the quotient. So what will happen is that the prover will divide the C of X by the vanishing and get the quotient, right? And then the idea is that these two should be the same, right? Left hand side should be equal to right hand side.
How is verifier?
It should be the same, just based on maths, right? Now the verifier doesn't have access to this. It's the prover that has access to that.
Verifier doesn't have access to
The C of X, because it doesn't have access to like the Fibonacci table,
Okay.
right? You know, it was the prover that was filling that in.
Yeah.
And likewise, the verifier has access to this, right? Because he knows where he wants.
Yes, yes.
So this one is with the prover, and this other one too is with the prover. So what happens is that the verifier does not tell the prover where he wants to. You know, Schwartz-Zippel lemma says that to check the equality of this, just pick a random point for X and evaluate it. So the verifier won't tell the prover the random points that they are picking yet. He will ask the prover to commit to C of X and Q of X.
What do you mean commit to C of X?
Okay, it's like I'm going to ask you to evaluate this polynomial at a point now, but I want to make sure that you don't change your polynomial when you see my point. You know, like if the prover knows what your R is, the prover can just like find a random C of X that will make this entire equation satisfy, right? Because he knows what V of X is also. So he can figure out what V of R is. Then once he knows that, he can just pick Q of X and C of X that will make the equation hold, right? But then, if you don't tell him yet, he doesn't know which R they are going to pick. So the only way he can do it is by being honest. Do you get? Like, he can try and change the polynomial, but based on Schwartz-Zippel lemma, if the two of them are not actually equal, there's only D points.
But how will the verifier know what to expect when he only has the vanishing point?
So it doesn't need to know what to expect. It's just going to like ask. So okay, let's stop using commit. Let's use what we are using in some check right now. So what will happen is that the verifier already has V of X. It will now tell the prover, okay, give me C of X and give me Q of X.
Okay.
Then me, I will now check it by myself.
Yes. And when you say this time, the verifier does not have C of X.
You will ask. You will ask now.
Oh, you ask.
You will ask. Yeah, you will ask for it. Yeah. So based on maths, there is no way that this will hold unless the prover is honest.
Yes.
If the prover is dishonest, then there has to be that R of X.
But if he's going to ask the prover for C of X and Q of X, what's stopping the prover from like tweaking it to what he actually sent before and then sending it over?
The problem I'm trying to say that you cannot tweak it to something that, like, if that was how it looks like, right? Like the prover cheated and then there's an R of X. There's no way by maths that the prover will just be able to remove R of X.
Yes.
Because if we are removing R of X, then it means that you have found another way to divide C of X by V of X that gives you another thing other than Q.
Yes, that's if it has a remainder.
Exactly. So it's like dividing 5 by 3, right?
Yes.
You are dividing 5 by 3, that's let's say 7. 7 by 3.
That remainder of
7 is going to be equal to 3 times 2 plus 1, right?
Yes.
So if this is the case, there is no way that, let's say the vanishing is 3, right? And then this is C of X.
Yes.
And then this is Q of X. And then this one is R of X. There's just this one, let's say this is fixed. There's no way that how do I put it? Wait, I'm coming. Feels like two things have to be fixed. I think the commitment will come in 2 steps. Like you'll send commitment to C of X first.
That's why we do the process section. Because the profile is going to evaluate C of X at a point, but he doesn't know what that point is.
Now you're talking about like something like KZG now. Powers of tau. Yeah, powers of tau. But now I'm just looking at like quotienting in general.
Yeah, as much as like there's a commitment, I say that commitment is fixed.
When you say
B of X.
like when you say commitment, are you saying like when they send that polynomial now to the transcript, is it like it's committing that polynomial to the transcript, or when the verifier sends a random point and say evaluate at this point, is that the commitment? Like what exactly is?
The commitment is like the Merkle hash. Like there's a way that the problem what I can't tell is that there are different ways to commit to a polynomial depending on the polynomial commitment scheme. So in like KZG now, the way you commit to a polynomial is that you evaluate that polynomial at something called the powers of tau. T
That's TAP.
The powers of what?
tau,
Now.
right?
Oh, so this is a commitment.
So if you evaluate it, you get a single value, right? That value is now the commitment.
Oh, so that's a commitment.
That's one example of a commitment. Another commitment, which is fry, is that you evaluate the polynomial at a lot of points, and then you just put them in a Merkle tree.
Yeah.
Then the root hash is the commitment. There are different ways to commit to. So it's fine. There are different ways to commit to a polynomial.
The power of tau, is it fixed or is it computed?
Power of tau is computed with the trusted setup.
So we can't set up a
You can set up the power of tau.
Is it like root of unity or something?
It's like powers of x. So like powers of tau is like, let's say x was equal to 4, right? It will be 4 raised to the power of 0, 4 raised to the power of 1, 4 raised to the power of 2, 4 raised to the power of 3, 4 raised to the power of 4, on and on like that. But it is hidden. Like nobody knows that it is 4. That's the point.
Powers.
So it's hidden. So the trusted, that toxic waste is 4. Like if anybody knows that that thing is 4, they can generate fake proofs. So they use like MPC to somehow like settle on 4, but nobody knows it's 4. Unless they all come together, then they will combine their shares and then they will not know that it's 4. But as long as one person is honest and he throws away his share, then nobody can. Yeah, exactly. So that time that Ethereum was doing all those, everybody was generating like a piece of this 4. and then they were combining it to get like just
So
one.
tau is not a number.
Tau is a number, but it's a number that nobody. It could be a big number.
So
That
it can be any number. That way.
yeah, it could be any number.
Why
So you can brute force the powers of tau, but then the field is so large that it doesn't make sense to try every single possible thing.
is that why it's called toxic? Because it is affecting
It's supposed to be hidden, and then if someone knows it, then they can generate fake proofs. So it's like toxic.
But when we evaluate this at the powers of tau,
That's the
we
common.
don't get one value.
You get one
Get-
value.
Because if you evaluate it and say first raised by 0, first raised by
No,
1,
no, no.
those
You
are
you
different.
evaluate it based on the degrees of x. So this will be like 2 times 4 raised to the power of 1, since it's like x raised to the power of 1.
Okay. If it was x raised by 1,
It was x squared plus x plus 1.
yes.
It will now be 4 to the power of 2 plus 4 to the power of 1 plus 1.
Oh, so it's just the x value that
It's just
is-
the x values. It's just like the powers of all the x values.
So what's in that the tau in it?
The tau is 4.
I know, like what's like why the name tau?
I don't know now. I'm not asking people that.
So, wait on, we are still in baby steps to GKR.
This is not what GKR.
Yeah, this is still baby steps to GKR.
GKR will start. It's supposed to start today, but it'll start tomorrow. Huh?
Well, let
Any questions? Does it make sense?
yeah, but still,
Huh?
I was struggling with C of X thing.
Yeah, you're still struggling with C of x.
Yeah, I'm for it.
C of x is the polynomial that is the polynomial that is equal to 0 if a constraint is met.
Right?
Yeah.
Or like,
But that division that he
Yeah.
was asking about, I'm still kind of thinking why, like,
yeah.
Why what?
why does that division, does it hold only when, does it hold when they are equal?
You're saying like why does it divide cleanly?
Yes.
Basically like we said that a polynomial can be written as the root. So that means that C of x, if you evaluate C of x at 7, it will be 0, right?
Yeah.
Whereas at 6, it will be 0. Whereas at something, it will be 0, right? So that means C of x is really like other roots, so let's call it R of x, but then times x minus 2, x minus 3, x minus 4, all the way to x minus 7, right? Because if you evaluate at 7, it will be 0, right? So it's part of the root.
Why is it other roots?
Like, I'm saying that C of x might not exactly be just x minus 2 times all the way to x minus 7. There might be other roots in C of x, right? But these ones are part. So when you now divide by v of x, which is just this part here, it will be clean. It's just cut. And then you're just left with this. This is now the quotient. Instead of calling R of x, let me call it Q of x.
No. Device of
Yes, it's like
Euclidean algorithm.
so, no, it's somewhere there, but it's not
You use Menda theory.
Nash equilibrium.
So, for that, the relationship about C of X will not hold for values above fields and above
Yes, it doesn't have to hold for those values
for those values.
Yeah.
Why?
because of. Let's say like the program could have just put anything at let's say f of 8 for example. So like there's a way that maybe it will just be 0. Maybe 0 also. Or it could have been 1. and this one could be, let's say, like 5. In those two cases, you have two different f polynomials, right? But the Fibonacci was still done correctly, right? Up to the points that it was supposed to be done. So you don't really care about all those parts. You just care about checking that in this range, you did things the way I wanted you to do them.
Okay, so basically, because we have these values as like our evaluation points, we add another one to give us a completely different polynomial.
But they share the same.
Yeah,
But both of those polynomials will pass this proof.
Yeah, we pass
Because
it
we're only vanishing.
at 7.
Yes. This is the time.
The problem was that just looking at C of x alone
Yeah.
as that small equation,
Yeah.
then adding x minus 7 down to x minus 2.
Yeah.
And I'm saying that if we divide everything,
Yeah.
in fact, you're saying that if we divide C of x with
Yeah.
a bound of 7, let's say it's bounded at 7,
Yeah.
and the denominator is the vanishing point 7 and 2 to give us 1.
If what?
C of x, right? The bound is at 7.
Okay.
Yes,
Yeah.
that's right.
Yes,
It's
that's
basically saying if C of x was basically like a polynomial with a bound of from 2 to 7, and you are dividing with the vanishing polynomial to also be a polynomial with bound from 2 to 7, it shouldn't be 1. Like the quotient should be 1 without any number.
If C of x is the same as vanishing.
Exactly.
No, but I think they said there are other. Let's say I put that R.
No, before that, like he wrote it down there, like, can you scroll down a bit? Yes, scroll up a bit. Yeah, this one. That Q of x should be 1.
Oh, it's only be 1 if C of x is the same as vanishing, right?
Yeah, that was
That's
But can you prove that
So
it
it
will
said
always
that
be the
C
same
of
as
x is
vanishing?
No, I'm saying C of x is bounded at 7.
But it's bounded at
Yes,
7.
it's bounded at 7. She was 1.
And then it's also bounded at the
two.
beginning, right?
Yeah,
Two.
yes.
And then to be
That's
1.
Wow.
It should be 1. I don't know if it will be 1 though.
Why?
Because of interpolation. You know, when you interpolate,
Okay, you are saying
Yeah.
like give us a 7.
you're supposed to be, when you interpolate, you're supposed to now be able to evaluate that polynomial at.
Different number of points.
Yeah. Which might have other roots. What I don't know is like if Lagrange interpolation always only gives you the roots. I don't think it will be the same. But we'll have to check it out.
Can we
What?
check it out? Let's do like round 4 or 3. And this will give us
Okay.
small.
So if we're doing bound 4, what does that mean? You have what? 4 points. That what?
F from F2 to F4.
I'm coming. How do we do this? I'm trying to verify the check. What do we actually want to check?
One check is
Are we starting with Fibonacci?
Yeah, let's start with Fibonacci.
Okay, so f of 0, that's f of 0. So we stop here, then it should vanish at 3 points, right?
Yes.
At 2, 3, and 4, right?
Yeah.
So we need to interpolate this polynomial. That's the problem. That's where the problem is come from. Because when we do the interpretation of this polynomial, it might be something crazy. Yes, like Wolfram alpha now. I should have implemented division. If I implement division, then I can just do it with fields. 0, 0, right? So this is f of x. See, it's crazy. But then, so what I was supposed to do now, I was supposed to take this f of x they were supposed to do f of x minus 1 minus f of x minus 2. So you get a new polynomial. That's the c of x. And that c of x, you evaluate it at 2, 3, 4 to be 0. But then we can't use this. We need something else to do this. So one way I could do, we could implement univariate division on the univariate polynomial. Oh wait, I can do this already now. We're not doing division yet. We're not doing quotient yet. So I should be able to do this with my code. I don't even get what I mean. Right. Can you guys see it? We can't do division, that's the problem. So f of x is alright. Our Fibonacci sequence was what? 0 what? 0, 1, 1, 2, 3. Is that where we stopped?
Yes. Yeah.
We stopped at 3. So this is f of x. Then given f of x, we should be able to generate c of x. Alright? Can we even generate c of x? We cannot. Because we're supposed to now evaluate f of x at x minus 1. Which is a polynomial.
Yes.
Not a field. Not a field number.
Let's pick the number now.
We're trying to generate like the full c of x that vanishes at all possible values of x in that range. So we should not be putting a constant
Value.
Yeah. We're not putting a constant value. Like obviously we could have done like c of x. We have done like c of x is equal to f of x dot evaluate, let's say 2, alright? But we already know that this works now.
Yeah, actually. Yeah, we know it.
So it's just useless. It's just useless. But I think it's fine. It's just like we need to wait a way to for univariate polynomial to be evaluated as another univariate polynomial.
Wait. Why do you say
That
you
line thing. Because we have f of x, and then we're evaluating it at f of x minus 1.
Yeah.
This x minus 1 is a. This x minus 1 is a polynomial, and x minus 2 is also a polynomial. So you need to wait for univariate polynomial to be evaluatable at another univariate polynomial. That's the only way you'll be able to get like the polynomial equation for f of x minus 1 and get the one for f of x minus 2. So you now have 3 different polynomials, and then you can now subtract them. That's when you now be able to get the polynomial for c of x itself.
I'm thinking why exactly you are saying invariant polynomial should be evaluatable at another
Like,
univariate.
when you did f of x, you had your trace, right?
Yes.
And then you converted it into a polynomial. You call this f of x.
Yes.
This is one polynomial.
Yes.
This is the one that is associated with this point.
Yes.
But then you don't know what this is, and neither do you know
Yes.
what this is.
Yeah.
So to get what that is, you need to evaluate this at x minus 1.
Yeah. Oh, yes. To get another polynomial.
Yes. Normally this takes a field element. So let's say f of x was 2x plus 1. Normally x is supposed to be a field element, but now you're saying x should be x minus 1. So this is now 2 into x minus 1 plus 1. That will be 2x minus 2 plus 1. That's 2x minus 1. So this is now what like f of x minus 1 is. So before we'll be able to test this out, I need to modify like the univariate polynomial to be able to do something like this.
To take in like
A polynomial for its evaluation. So that will give us another polynomial, then another one, another polynomial, then we can now do like subtraction and get C of x. Then we also need division so that we can be able to like get the quotient and everything. Bruh. Where did I get it from? It's based on Fibonacci. For which other one? That was also Fibonacci. Yeah. It's just like I just stopped at 3. I think we're good now. Information overload, bro. The only thing is just like Schwartz-Zippel lemma. You learned about roots, right? And then you learned like polynomials can be represented in root product form. And if you divide by root, you should divide like cleanly. But the main thing to get is like Schwartz-Zippel lemma. Alright now. Tomorrow. GKR. For those that have not finished their sum check. Oh yeah, that's even true. You guys will need to submit your implementations up to sum check. Yes. We'll create another form. Yes. So you submit it up to sum check.
When you submit just that,
Your repo, you should have univariate, Shamir,
not separate.
multilinear, and sum check.
You are still going to submit the same repo.
You can submit the same repo.
Different form.
But we need to review it. Because if you have a problem there, and you're trying to write GKR on top of it.
Why did you not check the file of the zero?
We'll do it.
We need to write text to make this easy for you.
Okay, yeah, that might make sense. Yeah, that might make sense.